Hi guys, so here we are. Well, I'm on my front porch. You are wherever it is you're listening to this, hopefully at home, being safe and smart. So we're gonna move on, and we have talked about arc length, talked about surface area, some nice applications of the integral. What we're gonna do now is move on to talking about parametrization, some polar coordinates, things of that sort. These, again, are topics that are going to be sort of foundational to some of the work you'll wind up doing in your Calculus 3 course. Let's start by considering this example here. So this first section is all about parametrizing plane curves. I know this is covered in our pre-calculus 2 course. Hopefully this has been something this isn't completely new to you, something you've seen before, but I'm gonna give you a little review here. So hopefully kind of fills in some of the gaps, helps you remember some stuff you might be rusty on. So let's suppose that a particle is moving along this ellipse, 9x squared plus 25y squared equals 225. Now, the first thing we might notice is that that ellipse doesn't allow us to have y as a function of x, okay? So it's not simply a case of identifying, some x value and being able to figure out what y coordinate goes with that. In fact, an ellipse fails to be a function, right? However, we might think about this in a different way here. And I don't know why this isn't opening, but that's okay. We're going to come over here to Desmos. So what's going on right now is we have a particle, and you don't need to worry about the way I parametrized it. For now, just think about the motion, okay? This particle is moving along this curve, and you can see round and round it goes. Okay, so that's its path. Now there's some big issues we can talk about, right? We could talk about how far it's traveled, right? There's a total distance. We could talk about rates of change, things like that. We'll get to those calculus issues, but for now, let's just think about what's going on here. We have a particle that's confined to this path. The path itself is not represented by a function. In fact, this fails the horizontal or the vertical line test. But I want you to notice something. The way this particle moves along the x-axis, if you think of that as the shadow, that little black dot down there as the shadow along the x-axis, then you can see, and I'll even pause it here, right? You can see that, right, this particle, right, casts that shadow. Rewind it, right? This particle is directly over that shadow the whole time. This motion along the x-axis can be considered a function. It can be given as a function. Similarly, consider its motion just along the y-axis. So if you imagine a shadow being cast along the y-axis, what would that shadow look like? Okay, and there it is. So together, we have these two coordinates. And so the idea here is that while the curve itself may not be given as a function, the individual coordinates, x and y, can be. A natural way to think of them as functions of time, right? We don't have to use time as our parameter, but it's a natural choice, especially when we're talking about motion. And so that's really the big piece here. The big piece is that while the ellipse is not a function, the x and y coordinates of the particle can be given individually as functions. So in other words, there's a function for its position on the x-axis, and there's a function for its position on the y-axis. Those functions do not have to be unique. But when you create two such functions, you get what's known as a parameterization. Okay. So here's an example. Let's say that we have some particle, and here are its parametrization. Notice the parameter is t. We have x equals t, y equals t squared. Well, identify its path and describe the motion. Well, in this case, if y is equal to t squared and x is equal to t, then a simple substitution of x for t gives me y equals x squared. And so we have this parabola. We also have a car that just drove by. So we have this parabola. Well, that's its path, okay? So its path is along the parabola y equals x squared. But we're also supposed to describe its motion. So in other words, how is it moving along this parabola? Well, and here's a good way to do it. If t is equal to 0, then we have the point, well, x is t, y is x squared, so at time 0, this thing is at 0, 0, okay? It's right there. Now, let's pick a later time, say t equals 1. Well, at t equals 1, x is 1 and y is 1 squared. It's at 1, 1. So how did it get from 0, 0 to 1, 1? Well, it must be traveling in this direction. And so when you hear about describing its path or its motion, you can just throw some arrows on this graph to indicate that it's moving essentially left to right in x, okay? And so its path is a parabola, and it's moving according to these arrows, okay? Here's one. X equals a cosine t, and y equals b sine t, and t goes from 0 to 2 pi. Well, let's see. If x is equal to a cosine t, then that tells me that cosine t is equal to x over a. Similarly, if y is equal to b sine t, then sine t is equal to y over b. Now, why would I do this, right? Why would I solve for cosine and sine? Well, essentially what I'm doing is I'm trying to figure out what its path looks like. And I'm going to do that algebraically. I mean, I could actually plot a whole bunch of points. If I wanted to, I could take and build a table. I could say, okay, here's time 0, and then here's my A cosine t, B sine t. Sorry, let me get rid of that 0. Could have a few columns here, right? Come back. Okay. Sorry, what's going on? Okay, here we go. T. And then I know that this is my x coordinate and this is my y coordinate, so I could surely plot some points, maybe the usual suspects, okay? Pi thirds, maybe pi halves, all the way to 2 pi. And I'd get a bunch of points and I could plot them and I'd get an idea of what this shape looks like, okay? So that's one option. But I'm gonna take advantage of some more analytic methods. And so why isolate cosine and sine? Well, that's because I know an identity, right? I know that cosine squared t plus sine squared t is equal to what? Yeah, it's equal to 1. Well, what did I say cosine was? Oh, x over a. So really, I have x over a squared plus y over b squared equals 1. Well, this should look familiar. What is this? Well, it's an ellipse, right? And so if you think about what the ellipse looks like, well, this is going to be A, negative A, B, negative B, right? Just remembering how to graph an ellipse. And of course, the way I've drawn this, the assumption is that A is larger than B, but that doesn't have to be the case. And then what we want to know is the direction. So again, let's start at t equals 0. Well, at t equals 0, the coordinates are going to be A cosine 0, B sine 0. Well, that's just A, and that is just 0. So here is time 0, right there. Now let's take a later time, but do yourself a favor, right? I'm not going to choose 1. I'm going to choose pi halves. Well, at pi halves, x, right, is going to be a times cosine pi halves. So now my x is 0, and my y will be, well, b times sine pi halves, or b times 1, b. So here it is at t equals pi halves. So I know my direction now, right? So the path is an ellipse, and the particle is moving in a counterclockwise direction, okay? All right, let's look at this one. A secant t and B tangent t on the interval negative pi halves to pi halves. Well, let's play the same game, right? I know that there's a Pythagorean relationship between secant and tangent. So I'm going to say, well, if x is a secant t, then secant t must be x over a. And if y, is B if y is B sine t, where did that sine t come from? Sorry. Y is B tangent t, then sorry, what's up with my pen here? Okay. Then tangent t is y over b. Okay. Well, what's the Pythagorean relationship, right? We know that tangent squared t plus 1 equals secant squared. All right, well, what did I say tangent was? Oh, tangent is y over b. So y over b squared plus 1. Let's see, secant was x over a. Oh, okay. So 1 is going to be x squared over a squared minus y squared over b squared. What is that? Well, it's a hyperbola. But how do I know what side? Well, that's where, right, that's where this comes in, right? Negative pi halves to pi halves. Okay, so we are over here, quadrants 3 and 4. And then maybe I shouldn't have put those arrows on the end. That was a little misleading. And then what's the motion? Well, how about 0? At time 0, where are we? Well, x is a secant t, which is just going to be right here at a0. And then how about we move over to, I don't know, how about, now I'm going to be careful here. I'm not going to do pi halves because remember, technically that's not a possible value for t. And furthermore, x isn't defined at pi halves. So I could do something like, I don't know, pi fourths. And if that's the case, then then x is going to be a over cosine pi fourths. And y is going to be tangent of pi fourths. Well, tangent of pi fourths, tangent of pi fourths times b. That's going to be 1 times b. And so, assuming b is up here somewhere, then, or positive, then we know that this is the motion of the particle, okay? So again, we have the path, that right side of the hyperbola, and we have the direction of motion. All right, well, here's an example. Let's compare and contrast these two parametrizations. So the first thing we might notice is that in either case, right, so for parametrization 1, let's say, x squared plus y squared is cosine squared plus sine squared t, which equals 1. So this is just the unit circle. And furthermore, which direction? Well, this is the standard parametrization, right? At 0, at time 0, we would have 1, 0. And at pi halves, we'd have 0, 1. So it's going around this way, okay? Well, let's look at parametrization 2. Well, again, we have x squared plus y squared equals cosine squared, oh, but this time 2t, plus sine squared 2t equals 1. Well, gosh, this is again the unit circle. With the standard position, right? This is 1, 0, and 0, 1. X is cosine, y is sine, so it's still moving counterclockwise. So they parameterize, their path is the same, but what's different? Right, this is also the unit circle. What's different? Well, we can see that we have a 2t here and just a t here. So what does that 2t do? Well, you know what? Let's go over to Desmos and let's take a look. So let's take x equals cosine t and y equals sine t. Whoops, that's not what I want to do. We have x squared plus y squared equals 1. Zoom in here. So there's my unit circle. And then what I'm going to do next is I'm going to have point cosine t sine t. Okay. And let's have this start at 0, and let's have this thing go to, I don't know, we can go around the circle a bunch of times, say 10 pi times. Okay. And so there it is. There's my point. Now, I'm also going to set up cosine 2t sine 2t. Whoops, I can type sine 2t. Now, right now, these are right on top of each other, okay? But watch what happens as we play this through. Oh, let's slow this down. It's a little fast. So again, my purple, I guess we don't need the coordinates. My purple dot is the cosine t sine t parametrization, and the red dot is the cosine 2t sine 2t. So what you can see is that that red dot is moving faster. In fact, how much faster? Well, let's see. 0 to 2 pi. Let's go to 2 pi. Actually, let's go to pi, about 3.14. So look what's happened. My purple dot, right, we've gone through pi radians. That purple dot has gone halfway around the circle, but the red dot has gone completely around the circle, which means if I keep this going, by the time the purple dot makes it around once, the red dot has made it around twice. So what's the moral of this story? That this parametrization, the particle is 2 times as fast, okay? In fact, if I only wanted to go around once, for one lap, so for one lap or one revolution, these t's would go from 0 to 2 pi, but these t's for one revolution, well, you tell me. Yeah, these t's would only have to go from 0 to pi. And again, look, 2 pi, right? 2 pi. Just be that 2t. Okay. All right. So now we want to be a little creative. So we have this lovely ellipse, and we want to parametrize it. Now, we've already seen that A cosine and B sine are parametrizations for an ellipse, right? That was up in one of our previous examples. Let's see, where was it? Right here, right? A cosine t, B sine t. That's a parametrization for an ellipse, okay? We want to build one with some additional constraints, right? We don't want to just put a particle in motion around this ellipse. We want it to start at a certain place, and we want it to move in a certain direction, and we want it to complete one revolution over the interval 0, 1. So let's think about this for a second. Maybe first get our hands on what this ellipse actually looks like. So if I were writing it in standard form, then we would divide both sides by 225. And when this reduces, we would get x squared. Well, how many times does 9 go into 225? So we would have x squared over 25 plus y squared over 9 equals 1. Let's draw this. Okay, so what this means is that that's going to be 5, -5, -3, and 3. Now, we want 0, 3 to be where it starts. So at time 0, we need this thing to be at 0, 3. Let's not worry about getting around one lap over the interval 0, 1. Let's just think about where we start and what direction we go. So if I want my x coordinate to be 0 at time 0, and I know that cosine and sine can be involved to parameterize this, then I want to use some version of sine, right? Ah, my pen. And I want my my y coordinate, right, to be some version of cosine. Well, let's see. At 0, I need y to be 3. So time equals 0 is going to give me a y right now equal to 1, right? But we really want it to be 3. And that means my x could be 5 sine t. Now, does this move in the right direction? Well, let's see. There's time 0. Where would this be if we were at, say, time equals pi halves? Well, at time equals pi halves, we would be at, well, 5 times pi halves is 5. And 3 times, oh, look at that. So we are moving in this direction, because that would be time equals pi halves, okay? All right, so right now, I've got where I start, and I've got the correct direction. What I don't have is the fact that I need this thing to go around over the interval 0, 1. Well, I think we can fix that. So let's mess with these arguments, right? So let's let x be 5 sine something t, and let's let y be 3 cosine something t. Well, what should we use? We know that cosine and sine, right? One lap around a circle or an ellipse is 2 pi radians, right? 0 to 2 pi, which means I could take that 2 pi and do this. Sine of 2 pi t, cosine of 2 pi t. Does that work? Because now at time 0, I'm still at 0, 3. And then what would it take for this to turn out to be pi halves? Well, that would be time equaling pi fourths, t equals 1/4. Oh, 1/4 would get me here, right? That's now time equals 1/4. Right? At 1/4, you get 2 pi fourths, which is pi halves. Same here. And so this parametrization is going to do the trick. Okay. All right. So those are some basic examples. Hopefully some of it's review. If not, it's okay. We're going to work through it. But again, what I would encourage you to do is go back, digest some of this, rewrite it, rework these examples on your own. And to be honest with you, it's not the easiest thing in the world, especially that last problem. It takes some thinking. So just be patient with it. The next thing we're going to look at is all of the calculus issues that are going to surround parametrizations. Promise my handwriting will get better. Apologize for that. It's not the easiest thing to see. I'm still getting used to writing this thing. I'm using OneNote, if anyone's curious. But the lecture notes will be posted for this section. And yeah, here we go. So the next set of notes to expect by Monday will be, if not on Monday, I'll say by Monday morning, will be the calculus involved around parametrized curves. And then on Tuesday, we will work through a lab together on parametrizing and the calculus involved. Okay, so please, again, I hope you guys are all doing well. I don't want to overwhelm you. Just, you know, we're going to get through this. Please stay safe, be healthy, stay smart. Don't go out. No trips for spring break. Jonathan Morley. And yeah, other than that, wishing you guys all the best. See you soon.